Okay, welcome back everybody. This is the second module in our 424 School of Engineering. Today we're going to talk about aerodynamics of 424. And I'm happy to see many people joining again today. This is for me an extremely exciting session. I'm passionate about aerodynamics and I really want to use this time with you today to dig into the details of what's happened in the last more than 10 years now of aerodynamics development that led us to the stage we're at today with 424. And to start with, I really want to to point out how much aerodynamics is an important ingredient of the performance of 424. And this is an extremely high level of development as well on this car. So I will explain that in details. I also hope my voice is gonna won't let me down because today I'm not feeling my best. Been coughing a bit, but anyway, bear with me, and hopefully we can go through this together. So the way it's gonna work is we are not going to do any theory again here. It's all about me presenting the details of how we've been developing 424, the tools. And by the way, every tool I'm going to show you, you can access. It's all public access for everyone using the links that I am going to use myself. So this is how Perrin works. Okay, so everything that I show you today, you can access yourself and dig into the details as well after this presentation. So before I'm starting, I'm going to start on aerodynamics. I'm just going to again spend 5 or 10 minutes on the big picture of 424. And this week I'm going to go through some slides again with you. So the website I'm using, as always, is this website, discover.perrin.com. You all have access to this website. This is where the modules and the material for today's module is as well, okay? So let's start with this page here, just reminding everyone what the goals for 424 are. And really the vision is that one day the 424 will win the hardest race in the world, Le Mans 24 hours. I've worked at Le Mans 20 years ago, and when I left to start my Formula One career, I said to myself, I'll come back to this race and I'll win it one day with my own car. So it all started there. And I absolutely love this race. For me, it is the hardest race in the world to win. You only have one chance every year. It goes at the speed of Formula One, but for 24 hours, it's the most amazing race. So 424 is a zero-emission car, okay? And we are going in 2 steps here. First, we have a speed challenge, which is setting a new lap record at the Nürburgring with our 424 battery car. So the version of 424 for the Nürburgring is electric with a battery. So it's very much like a Tesla road car in terms of architecture or Formula E car. When we go to Le Mans, this is what we call the endurance challenge for 424. And that will be using the fuel cell technology. So effectively, we're going to replace the battery by a hydrogen fuel cell. There will still be a battery in the car, but it will be of a smaller size. And the main source of energy and electricity will come from the fuel cell. Le Mans is getting ready to open a new category for hydrogen cars. They're saying it will be in 2027. That has already been delayed. Initially, it was going to be 2024. So we could imagine, we're waiting to get for them to write the rules for this category. But it's coming. And we will very much want to participate in this with 424. Now, the focus is on the Nürburgring. The status of the project at the moment is that we are hopefully this year getting from the digital phase, which was all the research and development that we have done for many years, and transitioning to the physical phase, where we're going to finally start building 424 for the Nürburgring. And that is mainly a commercial challenge at this stage. It's finding the partners that will come on board with us to make this happen. Okay. Obviously, the cost of just the Nürburgring project is significant, but it holds a lot of value as well. So I believe we are really well placed to make this happen sooner rather than later. Going into the 424 specification quickly. And I want to dive into some of the details of what the car is about. So everything that in terms of chassis, it's all bespoke and designed by Perrin. Okay, so we are not reusing any existing chassis here. It's carbon fiber all the way from from the nose of the car to the back of the car. It's all carbon fiber. It's very much like an LMP1 or Le Mans hypercar, if you like. But there's even more carbon fiber because we don't have the big engine in the middle. We have a longer chassis that holds the battery. Okay. The mass of the car will be 1,000 kilograms, and I'd like to keep the mass of the car at this level, no more. And about half of the mass will come from the chassis, and then half will be the powertrain. With the electric drivetrain, we still have challenges on the mass itself. The battery is fairly heavy, and we are working hard on that. But I believe we are going to achieve this. We're going to use Formula E motors, one at the front, two at the back. Each motor is capable of 300 kilowatts. So the total power potential for the car is 900 kilowatts. And then the battery is what limits the power of the car. We have a target for 800 kilowatts, which is more than 1,000 horsepower in old currency. And there is a lot of work actually happening as we speak on this battery specification. It might be that the first version for the Nürburgring will be slightly lower on power than 800 kilowatts just because of the technology available to us. But again, we are working really closely now with the battery supplier to work out a good solution for us. Obviously, when the motors are capable of more than the battery, we have the ability to play with the balance of power. So how much we send to the front, how much we send to the back. So this is very much an important part of our strategy for performance. And that's what we call the active power distribution front to rear through the corner. So depending on the state of the car, and I'll dive into this when we do the vehicle dynamics module, I believe next week, into how we play with power distribution front to rear. So we are not going to go into details today on this. The transmission is a four-wheel drive, front and rear-wheel drive, obviously, and single-speed gearboxes. We don't have one motor per wheel. What we have is a motor driving a single transmission each end of the car, a differential, and then drive shafts going to each wheel. The energy for the battery is about 50 kilowatt hours. It might reduce a bit. Actually, we are using more like 45 kilowatt hours on the 800 kilowatt specification for the lap of the Nürburgring. And one of the fastest accelerating car on the planet. We are not designing 424 to achieve 0 to 100 kilometers an hour from a standing start to be the fastest in the world. It's all about the lap time around the Nürburgring. So obviously there will be faster accelerating cars out there, but overall it will be the fastest car ever, zero emission car on this track, and hopefully even beat the Porsche 919. The top speed is 360 kilometers an hour. We actually have a speed limiter on the car. We don't want to go over that speed. Otherwise, we'll go over the rating of the electric motors with the single speed transmission. And also, the tires are not made or designed to go faster than that speed. And it will also consume too much energy. So we have a good optimization strategy around these top speeds. And it's quite an important number we defined early on in the project. Now, a bit of aerodynamics, and we're going to dive into that today. We've got movable aerodynamics front and rear. So we've got a DRS at the front and at the rear, and I'll explain why we have it both ends of the car. And I think if you read a bit what's happening in Formula One for 2026, they've discussed this exact problem as well. The need to have movable aerodynamics both at the rear and at the front, not only at the rear, to make sure the car is balanced, even when you're in the low drag downforce mode. We're going to use electric power steering instead of hydraulics because we have a lot of electric power in the car, and that saves us from using extra systems. Okay, and finally, as you all know, where Perrin exists and how you can join the team. So Perrin.com, I'm sure you are all familiar with it now, but I want to always explain a bit more about what Perrin.com is. So I'm going to click here. And this is very much the dashboard to the core team's activity. And this is where you find our next meetings. So in fact, we are now in the 4-to-4 school meeting. You find join buttons here. Anybody can access these meetings. You don't even need an account to access these. We also have our core team meeting every week. The next one is next week. And if some of you want to attend, you can as well. Listen to what we are developing. We also do this we have contributors coming in to help us fund some small projects like this 4-to-4 simulator we are going to install at a university soon. And you can all participate in this. And if you click on contribute here, you will have all the explanation of how this works. And also you can follow some discussions we're having on the daily basis with the contributors and the core team, people who are active, again, every day, our test drivers, our software developers for the dynamic simulation. I write there every day on all the activities that are going on behind the scenes. And actually, it's not behind the scenes in this case. It's for anyone to see, because Perrin team is an open team and transparent team. Then you've got the WhatsApp community, and I know you are part of this community if you're here today live with us. And this is a great way to interact and have this conversation fluid, and just make sure everybody's on board with the School of Engineering and some developments we're doing as well with community members. Some of you might follow. We have a small group of people working on some software development around speed estimation of the car as the car goes around the track, using an AI tool that we are developing, and other developments around the battery models as well. So we're going to use WhatsApp more and more to drive some activity for the team with the community. And finally, on social media, we are very much on LinkedIn. And I'm starting to put videos on YouTube. In fact, this will go on YouTube later today or tomorrow. So yes, we're going to start spending more, investing more time with videos on YouTube. And to remind everybody, the reason we're here, and I do what I do this way, is I believe that Perrin is here to help the world become a team. It's all about the team. It's all about the machine that builds 4-to-4, that builds the machine, and this community that you're part of, and creating this new experience for everyone. Okay? Before I start the aerodynamics module, if anybody has a question about what I've just explained, please raise your hand and let's start a conversation. Okay. Rain? You got a question?
I'm sorry, that was a mistake.
Okay, no problem. If everybody's happy, we are going to get started with the module now. So you can find all the material on the 4-to-4 School of Engineering modules and aerodynamics today. Okay. And we're going to have a number of sections. It will start with a little bit of history of how Perrin started from an aerodynamics development point of view, some 13 years ago now. We're going to go through the process I use when we do CFD development, starting from the CAD model in Onshape. going to some CFD results and showing you the tools we are using and the platform to develop 424, and also the access. Here you've got direct access to the logbooks where we have all the runs, all the CFD tests one by one, logged and registered, so you can see the progression of the development we've made. After that, we go to building an aero maps for the car, aerodynamic maps, which is basically taking a summary of the CFD testing for the specification, for the latest specification of the car, and building a model that will then feed into our dynamic simulation, which is the 424 VPP simulation in Unity. For those who are not familiar, again, there's a video about it that we did last week, but I'll keep talking about this simulation. And this is where the aerodynamic maps is used to model the behavior of the car dynamically around the Nürburgring lap. Okay. So let me start now. And one thing I want to say before we start is I have worked on, Le Mans cars, Formula One cars. I did the Neo EP9, which was this electric hypercar a few years ago. And 424 is actually the most performant car I have ever worked on. It's got an aerodynamic efficiency of 5.5 to 1. So 5.5 unit of downforce for 1 unit of drag. Now you're going to say, but okay, Formula One is much more developed and there's much more resources around. Absolutely. Obviously, Formula One is restricted by the regulation a lot, where 424, in this case, for the Nürburgring, is not regulated when it comes to performance. We are following the regulations for safety, but for aerodynamic performance, we are not under any regulation. So that has allowed me to develop this car to a higher performance level. To give you a comparison, the Le Mans hypercars, the current ones racing, they've got an aerodynamic efficiency closer to between 4 and 4.5. And then Formula One will also be around that area. Obviously, it depends on your drag level. Formula One is at a higher drag level than Le Mans, which means more downforce, more drag, but at a similar ratio. And what we're doing with 424 is we are actually higher on drag downforce, but especially on downforce. Okay. I want to say that because of my background, and when I came out of Formula One to start Perrin in 2011, I came out of being an aerodynamicist for a few years at Williams, and I basically starting the company Perrin in 2011. The first point of focus was aerodynamics. I invested what we had as a capital investment into CFD, and the first task for me was, let's design, and I'm going to show you here what it looked like at the time. Bit of history here. Let's design a car, which at the time I used to design in NX. Now I design in Onshape. Let's start designing a car from scratch and then put it in CFD. I contacted TotalSim, this company in the UK, because I had one of my colleagues at Williams also left Formula One to work for them, so I had a contact there. And they're providing very high-level CFD solutions for Formula One and the motorsport and automotive industry. And the first investment was getting CFD capability for the Perrin project. So I bought a cluster. In fact, I brought it to my house. It only stayed there for, I think, 2 or 3 weeks because it was creating so much heat and being so noisy that we just realized it's not possible to keep this in our house. So I basically asked TotalSim to get that cluster back, and then I could access it remotely, which I did. And I was running CFD on my own. So between the years of 2011 and 2018, to be fair, I stopped a bit earlier, 2016, on that first development path. I was designing and running CFD on my own. So I needed a tool that would allow me to do about 3 or 4 tests per day. And all my time was spent into designing a new test, So first, having a complete car designed, something that was ready for CFD, and after that, doing iterations on my own, and then running the tests, looking at the post-processing, and making a decision on what I wanted to test the next day. And I'll show you the logbook and how many tests I've done. I think it's about 2,300 tests over a period of 4 years. And honestly, it's been the biggest learning opportunity for me in terms of aerodynamics. In F1, I learned a lot, obviously, going through to the wind tunnel, but doing the pairing project for 3 or 4 years this way was so intense. You know, I had to, every single test, I was analyzing it, and I had to do front of the car, back of the car, floor, everything. So I want to show you a quick video here. That's quite a funny one for me to watch. So let's have a quick look. So this basically shows, this is basically the last slide, between 2011 and 2018, using what we call the unit tests method, which is what we do in Formula One. We change one parameter at a time. If it's better, we keep it. If it's worse, we don't. And we keep progressing this way, okay? So this video is putting all the baselines, so all the intermediate steps together, and showing you how the shape of the car has evolved from the first baseline that I designed to the last one in that period of time. And you can see here, it's not even looking like 424 because we had more developments happening 2 years ago, which I'll show you in a minute. So I'm going to play this video for you. Just have a quick look. Let me pause here for a minute. So what you see here is run number 0257. And I only filtered through the baseline. So there are more tests done, but I'm only showing here the milestones. So each time we have a new baseline where I put together the latest improvements and build a new best version, if you like. So it starts from run number 1 to run 2000 or something like this. And you can see each time it's just one change or 2 changes at a time. You see, at this stage, I added a roof on the car. Initially, the car was an open cockpit. Because I was working to develop an LMP1 for Le Mans rules at the time, and it was cheaper to build an open cockpit car than a car with a roof on top. And I thought initially the open cockpits will be the compromise between cost and performance will be in favor of the open cockpits. But actually, when I added a roof on, the performance was so much better, not drastically better, but enough to effectively realize this is the way to go. And at the time, there was 50% car on the grid that were open and closed. Now all cars are closed. So that was the right thing to do. I think there's a question from Berken who's raised his hands. Do you have a question?
I was just wondering, is there any risk of reaching a local max optimum when you're doing just one part at a time, or do you have a way of working around that?
So if I understand your question, so you're saying, yeah, so reaching a local optimum and not being able to exceed that area and then not seeing a bigger potential somewhere else is what you're saying?
Yes, exactly.
Yeah. So to be honest, this method is exactly what Formula One is using for years now, and I tend to agree. So yes, to answer your question, yes and no. So yes, because and you see when you follow Formula One these days, everybody talks about the concept. The concept is basically what is your first iteration looks like, and after that, all you do is do these step changes. You know, you try one direction, the next, just one parameter at a time. And what you're doing is basically converge to an optimum solution for that concept. But what you may miss is a better solution with a different concept. So yes, you're right. And this is why the decision on the first design as a concept is so important. It doesn't mean it will be the best car aerodynamically, but it will lock you into a path of optimization. So people with, and that's where you need experience, because the definition of the concept is done by the most experienced people in the team. And they will say, we are going to optimize this concept, because we don't have enough resources to optimize all the different concepts that we can think of. And I did the same with Perrin. I had an idea of the concept I wanted to optimize. So I did the first version, and then I went to optimize that. You're right. You might miss on a better concept, but you will not know it before you optimize your own concept and see how far it goes. In Formula One, you can see some teams are better at that than others. And you can see the teams at the back, they can't develop out of their concept. It's very, very hard, and to then close the gap to the teams in front. So yes, I think your question is you're absolutely right. Does it make sense?
Yes, thank you very much.
Okay, you're welcome. So yeah, I had thanks for your question, and anybody else want to jump in with a question, please don't hesitate. So yes, I very much had an idea of what I wanted, and then I just let the process guide me to or develop to the optimum. As you can see, the front of the car, I always wanted something fairly open, so with top and air going over and under the splitter or the front wing. That was something quite important for me. And then some sort of simplicity. There's some cars at Le Mans that plays a lot with air going back in on either side of the rear wheels, but I never did that. This is like a conceptual idea that at some point you're like, no, I'm gonna commit. You need to commit to an idea that you've got based on experience, and then develop it as far as it can go. I'm gonna keep playing that video just a little bit more, and there's a couple of points I want to make. So I've removed the roof. The reason I've removed the roof at this point is because we happened to, in 2012, so a year on, we worked with Pescarolo, a team at Le Mans, to do a car for them. And what I did is I blended, and we had to use the Aston Martin LMP1 chassis, which was open. So I reintegrated that chassis into our aerodynamic concept. We had to reuse the rear wing as well from the Aston Martin and the floor, but the rest of the car was new. So what I did is from the complete new concept that I had invented, I replaced with I put the Aston Martin chassis in, the rear wing. That car, to be honest, was in 2012. Unfortunately, we started off the Aston Martin LMP1 car, which was a bit of a failure the year before. With Pescarolo, we did a completely new aerodynamic package with the images you see here. So I did that, and we changed the engine as well. And the car went 8 seconds faster at Le Mans compared to the Aston Martin the year before. The engine was a part of it. The aerodynamic itself worked well, but we had some issues at the front, and I'll be honest, it didn't work as intended. We had some issues as well from our side, which we've learned a lot from. And it's something that the learning from that is carrying over into 424 today. So we will not have these issues now. But that's the reason why we went back to open cockpits. So the car you're seeing now is the Pescarolo P03, we called it. And you can see there's more details on the chassis. This is the Aston Martin nose and the chassis we had to work with that we couldn't change. But that's in the history of Perrin, okay? And this is now, you can see the car is fairly consistent now. It doesn't change much because we are going into the last details of that car. After that, the project was finished with Pescarolo. We come back on the drawing board, and we basically, we started with the closed cockpits and continued the development of Perrin for the long term. Okay, so towards the, now we are run number 1467. Right. And this is more or less the end of this development phase. At that point, the car is closed cockpit. It was still a hybrid car, so petrol engine and hybrid electric. Not an electric. It was not 424 at the time. It was the LMP1 project. Ran out of investment for CFD, so we stopped the development. But I wanted to show you this video to just give you an idea of how cars are developed. Okay, it's decision on concept and then one change at a time, and go from there and push the performance as far as you can. The other thing I wanted to show you a bit using this video as a last point, this is something I've got really close to my heart, and I want you to try and understand what I'm going to say here, but it's based on my experience. If you look at the starting point, I go back here, versus the end. If you do sections of this car, this is what I call an all-rounded camembert, if you're French, melting sort of shape. Because from my Formula One experience, we had so much time to surface the car, and in a way, we were asked as well to create shapes that were all rounded. If you do a section of the side pod here, you'd see a lot of curvature. It took me a lot of time actually to design this sort of surfaces. Look at the chassis, it's got variable blends. The nose is fairly surfaced, so a lot of patches. I thought at the time, so please, this is an important point. I thought at the time that this was what aerodynamics should be like for performance. But the time it took me to design this it took me too much time, and to maintain it and to develop it was complicated. Because you can imagine, say I want to just raise the side pods by 25 millimeter, which is typically the step I would do to try and see the sensitivity of that. Was very complicated. It was very complicated to modify these surfaces. And remember, I was trying to do 3 tests per day. So I thought, okay, what if I simplify, I reduce the number of parameters to build my car, to design my car. I go down an order of magnitude in terms of number of parameters. So instead of having all rounded surface side pods, if you look at the end, here we have, if I do a section across, you'd have a straight line, a constant blend, a straight line, constant blend, straight line, and that's what we call maybe a boxy design. But the process of, it took me 4 years to go from an all surface design to a box design. But every step of the way, I made sure the performance remained the same. And in some areas, I actually had a better performance. And if I would lose performance at the one section of the car at the time, just to make sure performance was not lost. On average, I didn't lose any performance. What it gave me is the ability to very quickly, with only 1 or 2 parameters, radically change a big surface of the car. So now to raise the side pods would take me half an hour in CAD instead of 4 hours or 5 hours. And the value, and really this is an important point for me, we're into motorsport here. It's not about creating class A, beautiful surfaces that will look nice to the eye up to a point. And for me, actually, what looks nice is what is fast. But the important point for me here is how fast can you develop? How fast can you iterate your design and test a new version of it? That's much more valuable in motorsport. So coming with this, I call it the design philosophy, something easier to, it's easier to have a cube and pull the faces than having a very complex shape that you're trying to offset, if you see what I mean. Increase the volume in some areas. So we are engineers working towards performance here. It needs to be structured and it needs to be easy to develop. And that's the biggest learning for me of this design phase, which I will carry all the way to the 424 and beyond. It's this building a toolbox that is very easy to develop for yourself and for the team. And by the way, I love seeing today that even in Formula One, if you look at the Red Bull that's at the front of the grid versus a car at the back of the grid, that my eye has been trained to recognize some areas of the car, how they're designed, how many patches or how many parameters it would take to design it the way they do. And if you look at the Red Bull, some parts on the top of the chassis is very much an extrude. It's not variable blends. They don't spend as much time. They've done the same because I think they've realized it's no point spending energy and time in building complex CAD models. You need the essence of performance, and you need something that can be, the floor might need much more surfacing than the top body. So if you look at their side pods now, and especially the top part of the engine cover and the cooling channels, they're actually fairly structured CAD designs with less parameters. Okay. Any question on this before I move on? Yeah, Bautista, please.
Yeah, hi. I have a quick question. So would you say you have gone through two different concepts in this case? And if not, what main features you want to keep in your concepts, let's say?
Yeah, so I have been through actually more than one concept here because there is the change of philosophy of how the car is designed. So yes, I went through a change of concept in terms of underlying the foundations of the CAD of the car. If I look at this, I'm seeing 1,000 parameters. If I look at this, I'm seeing 100 parameters. But the performance is much higher on this because obviously it's gone through optimization as well. But the other thing is in terms of concepts, at the beginning, it's hard to see on these images, but I'll try and explain. I wanted to, so the air going under the nose, so that red area that you see here. If you'd see the wheel arch, it was actually closed inside where the suspension legs are coming through to attach to the chassis. The wheel arch actually was an idealized surface that was sealing the suspension legs going through. So it was creating a very smooth channel for the air to go before it exits at the back. The idea was I'm trying to isolate the air from the inside of the wheel arch, so the air couldn't go inside the wheel arch from under the nose, if you see what I mean. That was a mistake. That was a concept that dictates that the airflow will work in a certain way, and then you optimize around that. I carried this concept over to the, I'm glad we're talking about this, to the Pescarolo Aston Martin car, if you remember the story. So on the Pescarolo, that concept was still in. When we went to build the car, I said, we have this surface and the suspension has to go through. I want this to be, and obviously the suspension goes up and down. We need to find a way, guys, to create a seal so the air cannot pass through that surface. Spend a lot of energy. We built some rubber boots that would, attach to the suspension and deflect, so it would effectively create a bit of a wall. The reality is creating these systems is extremely hard to not have any leaks. And we didn't find the downforce at the front that we wanted on that car based on CFD, because when you go to the real world, to build something that geometrically works as a seal, they do it in Formula One on the brake ducts, where the suspension goes in. They have some really nice seals there. But for us, we didn't have the right knowledge and I would say know how to, and we lost performance that we thought we would have. Based on that learning, I went away from these concepts. When we started with the closed car, this one, I completely opened. I basically I cut a big hole. The suspension had the space to go through. We lost performance initially, but actually when you redevelop around that concept with turning vanes and things like that, the performance was back up, but it meant that it's a concept that you can deliver, you can build. And that carries on to the 424 car today. So yes, I have changed concepts based on, but you see the cost, you see how long it takes to learn. these mistakes, and this is why experienced engineers in Formula One hold this sort of knowledge and then know what concept is worth developing, what is not worth developing. Does it answer your question?
Yeah, definitely. Thanks.
Yeah, no problem. Another question from Axel.
Yeah, hi. Do you hear me?
Yes.
Yeah, I have a question. Because your primarily like focus was aerodynamic, how do you manage like throughout the design, like the packaging of like heat exchanger and stuff? Like
Yeah.
you need to carry that through the design, and I guess like your primary concern was aero. So how do you deal with that?
Yeah, thank you. Yeah, good question. I was lucky that I came from being a race engineer as well. I had experience at the track. When you're race engineer, you're very much, one of your main concerns is the cooling of the car and make sure the brakes can cool properly, which if you haven't been at the track, sometimes aerodynamicists, we can lose focus on these things and just look at downforce and drag. I was lucky that I had been around enough. So, well, not enough because I just explained that I made a mistake on the front aerodynamic concept. But on the cooling, for example, this is something that I had very much an understanding of, dimensions for radiators. I had worked at Le Mans in an MP1 with Courage before as well. I know the sort of heat rejection from the engines, V8 engines, V10 we used to use at the time. So I put the radiators in the model. So in the aerodynamic model, we have radiators, and I wouldn't change the size. I would make sure there's enough radiator and heat exchanger flow. So we have in CFD, we have the air coming inside through these inlets under that panel here that feeds into the radiator. And in CFD, we measure the mass flow of air. And I had an understanding of how much mass flow we need. So for every test, I still make sure there's enough cooling air going into the car. And the same for the brakes, cooling the front brakes and the rear brakes with this duct here. In fact, this duct was not working very well. The latest, the 424 one is much better. I think because of this shape of, of side pods, reducing the top pressure and not feeding the air properly. But actually, if you look at the initial concept, it was worse. We had an intake here for the rear brakes. I overlooked some areas. The rear brake cooling was not good enough on this sort of brake inlet. When we did the the Pescarolo car, the rear brakes were too hot. We didn't have enough cooling. You see the intake was there. That was not working very well. So as an aerodynamicist, if you don't have the experience, you need to work with someone who will say, we need this much cooling. We need this much airflow coming in for the brakes, for front and rear, for the engine. So yeah, absolutely, these things are important.
Thank you.
Okay. Any other question before we move on to the next section? There's quite a lot to cover. So let's move on. So I'm really happy I was able to show you that piece of history that always will belong to Perrin and explain where we are now. Obviously, the car now is very different, as you can see, but carries the philosophy. But can you see how structured the design is? I had people coming to me saying, looking at this, saying, oh, it looks nice, but we can't wait to see the developed version of it. Like the way it is all rounded and, oh, it's very boxy. And I'm like, yeah, exactly. This will always be like that. And this is a 5.5 to 1 ratio on drag over downforce over drag. It's very high level of performance. And it's like Apple products. It's like the iPhone. It's like your MacBook Pro or whatever it is. It took them years to go from rounded to flat products that does just what it needs and is efficient for the user. And in this case, the Perrin cars will always be designed this way because I've learned this is the right way. It works for us. On this picture, you can see the DRS front and rear. So we have the flap at the rear, like an F1 flap that's moving, and the front as well. So you've got the front we call it the front wing. They call it splitter on these cars, but it's very much a front wing with 2 elements, and the flap moves. Excuse me. So when we open the flap at the rear, then the flap at the front drops. So the hinge point is at the front, and the flap drops. So we reduce the drag by about 30%. The downforce reduces by about 25%. And we also reduce the front downforce to keep the car balanced. Everything I do is done in Onshape, and all the aerodynamic model is in Onshape. So if you click here, okay. And again, everyone can access this model. You don't need an account, which is fantastic. I keep saying that, but don't underestimate the power of this access to information now through tools like Onshape, especially for projects like the pairing project. So this is what we call the CFD assembly. This is the assembly I take to CFD now, direct. And it's made of sub-assemblies. So you've got the body assembly. Let me make this bigger. Okay, that's nice. You see the body assembly has, the radiators we spoke about. Well, this is the radiator duct, inlet, and then there is a surface that covers the radiator area, and that will be there to measure the flow through the radiator. That's actually covered in a different assembly. Each assembly holds a name for a CFD property. So when you need something that will have a different property and need to measure a mass flow, it needs to be in a separate assembly, and it's called the TOINT in the CFD world we are using. So that's why it appears in a different assembly, just as a surface. That's the surface in CFD that we're going to measure the mass flow of air through. You've got all these little surfaces that are measuring the mass flow to the brakes. So if we go back to the main assembly, you see all of them here. I can isolate that. You can see that we are measuring the mass flow going to the front brakes through the inlets here. So all you need for CFD with our methodology is this assembly that covers the body of the car, the splitter. The reason we separate the splitter from the body is it will have finer mesh properties. There will be more cells around it because it's a faster flow and closer to the ground. So we call it splitter. We also separate the flap of the front wing, also because it's got different properties because it can rotate. So in CFD we have the ability to move flaps. So we don't have to do it in CAD all the time. If the flap itself doesn't change in geometry, then we do it in CFD for ease of use. Then we've got the rear wing. Here, the underfloor. Okay, and that covers the details of the fence under. So that also has different mesh property in CFD. All the toe-ins are measurements of mass flow. And the suspension and wheels is also a separate model. In fact, it's not completely accurate in this assembly. We even have to separate the wishbones to the wheels. It's much more segmented because the CFD will manage the suspension movement. So when we change the ride height of the car, automatically the wheels will go up and down relative to the car, and the wishbones will also rotate in the correct way. So we manage everything in Onshape. The other thing we manage, and I'm going to have to sign in for this, so I believe if you want to see that, you need to create an account. So let me go back in the documents. So what you see here is the version control system for Onshape. You see versions and history here. And you see version 177, 176. So we are managing versions of the car We also have branches, which are, so you've got the main tree with all the versions, and then you've got branches on the side, which are tests. They're going to work or not. So we do a test, and it's called a branch, so it's a B number. And typically we will test one change, and if it's better, we're going to create a new version using that change. Remember, it's called the unit test methodology. So you can see here the history of the creation of this document from version number 1, which was 2017 in this case. So you see, after I had done the first LMP1 study that with the video I presented, at the time it was all done in NX Siemens. I had a complete rework on our methodology, and I shifted to Onshape. I redesigned the whole car in Onshape in 2017, 7 years ago now. And since the car has been developed in Onshape. We could look at version 1 actually for fun, but that assembly wouldn't exist. I will show you other versions. And you can see like version 122. So in 2020, 3 years later, we've got 122 versions. And we started doing CFD again in 2022. And I will show you the results and how this all worked. So in 2022, there's a lot of versions. You can see here 2022 version 145. Each version in this case is associated with a CFD test and a branch as well. You can see a lot of after version 145, we've got 1, 2, 3, 4, 5 branches which are unit tests, and then maybe 2 might be positive. So we combine them into a new version for the new baseline, and then we keep going. That was very much a CFD development here. Branches, and then new version, and again. The cool thing with Onshape is you can compare versions. Let's have a little go here. So let me well, before we do that, we'll have to go to Bramble, see the CFD results, and then we'll look at a specific case. So I'll keep this open here. And I come back to our documents. We've got a comment here. Thank you. Okay. So I've explained to you what we're doing in Onshape. When you're in Onshape, just to finish, we will go here and export to go to CFD. We don't export the whole assembly. We are going to export individual files for each assembly. So if I have made a change in the body relative to my baseline, I'll just go and export here. And I basically export an STL file, which is basically a triangulated version of the car. So we triangulate the car here because the CFD software doesn't understand CAD. It only understands triangulated geometry, so it can mesh on top. And we're going to basically use the fine resolution. So we tested at different coarse, medium, fine, or custom, but fine is working well in this case. And we're just exporting that assembly. And we are going to upload that assembly into Bramble for CFD analysis. And Bramble is organized the same way. The car is divided in assemblies the same way as we have it in Onshape. In the future, there will be an API link between Onshape and Bramble. So I will not need to download the geometry and upload into Bramble. It will happen in the clouds automatically, which will save time and just make data management a bit more straightforward. Okay. Any question on the CAD before I move on to CFD results? Okay, let's move on. So now we've got the CAD sorted. Let's go to the exciting bit, the CFD results. Before we do that, just for fun, I want to show you a little side-by-side comparison of, so this is 424 in 2020. So we had, the first CFD, the 2,300 runs were finished 2016. 2017, I redesigned the whole car in Onshape. I don't have at the time the resources to do CFD testing, so I make some modifications, but based on experience and thinking, we'll test that later in CFD. But that's what it was very close to the last run that I had done in CFD. But the main goal was, let's do a new, completely brand new CAD model that will then be used to develop further. And that's the 424 that we call, the Le Mans optimized car. And in 2022, we got some investment in from one of our members, Cameron, and thank you, Cameron, again for that. And we did optimize the car for the Nürburgring, because the aerodynamic demand for the Nürburgring is quite different from Le Mans. And this is the car here. And I'm going to switch, just for a bit of fun here, I'm going to switch to that side-by-side view, and we're going to just have a look together at what it looks like. So let me switch view. Okay. So I'm going to Unity here. Okay, everybody can see that. So we're into Unity, our dynamic simulation software. And we left the LMP1 car on the side. This is now the car that's driving the Nürburgring one. But I like to use this just to explain what we've done in 2022. The main goal was to go up on the polar of the car, which was increasing the drag level, as we say. Think about it as going from Monza in Formula One to going to Monaco. So we needed a 30% or even 35% increase on the drag of the car with the associated downforce and more. The Le Mans car was still under the regulation of Le Mans. I'm going to try and center this a bit better. But suddenly we could go and develop like Porsche has done for the 919 under no regulation and go a bit bigger on the wings, for example. And that helped a lot to achieve that increase in drag and downforce level. First, some things you will notice, and that's like general aerodynamic rules here. To go from a low drag down car to a higher drag car, it's not only the wings. Obviously, the rear wing here is much bigger, as you can see. That is a big part of the equation. To rebalance, we needed a bigger front wing. So if you look at the size of the front wing, actually has been increased towards the front, but also the flap is more aggressive. If you, I'm trying to give you a better view here. If you look at the flap, actually was on a low angle setting. You see the flap at the back. The flap now is on the higher angle setting on the 424, but also the general curvature of the main plane in front of it is more aggressive under the car. It's changes that are a bit hard to see, but the front wing will produce, about 30% more downforce in this case. Also the floor, we can look under the cars here. The floor is different. We've got a much bigger volume under the car here in terms of diffuser. This was still regulated by Le Mans. We went higher on the trailing edge and completely reworked the floor. The kick of the diffuser starts a bit earlier. I trimmed the front here. We've got more volume in this area, which was better for performance as well. And then if you look at the top body, which is like the obvious parts that people can see and comment on a lot, but they do a bit, but not as much as the front and rear wings. But if you look at the wheel arch, for example, the front wheel arch is we call it much more volume. There's much more volume in front of the tire and behind. You see how much shorter the wheel arch is in front and behind. When you do that, it's quite powerful, actually. When you reduce that volume, straight away you create pressure that is pushing down on the splitter or the front wing. It will create more drag straight away. You've got more pressure in front of that face where the lights will go. Well, there's no lights on the 424 for Nürburgring, but you see that volume I'm talking about. So straight away is more downforce, more drag at a ratio that is powerful enough that we want to have it. And the same goes for the tail of the wheel arch. So the tail here, when you reduce the tail, you're basically allowing the floor to have more surface that is basically seen by the air and pressure applying on. But that will come with drag as well. And then you've got things like, you see this fence, triangulated fence at the exit of the front wing air. That will create pressure again on top of the floor. That fence is very small on the Le Mans car, just to allow the air to come out without creating that pressure. Okay. Other changes, the rear brake cooling is higher at Le Mans. For the Nürburgring, we have less demand on the rear brakes because the lap is short and then we stop. For Le Mans, we need to have, for very high ambient temperature, we need to have the ability for the race to open fully to have more rear brake cooling. At the Nürburgring, we'll set a record a day where the ambient temperature is fairly low. So we can push the cooling down a bit. Other changes is the roof is a bit lower on the 424 for Nürburgring compared to the Le Mans car. This was more to do with just the packaging inside the car and reducing the center of gravity and things like that. So it's not all aerodynamics. The last thing is you see these big holes on top of the front wheels for Le Mans. They're smaller here. They're creating drag, and they're here for safety in terms of if the car goes into a high-speed yaw situation, and to avoid the car from taking off from the pressure under the wheel arch, Le Mans is asking for these holes to be there. There's also some at the back on the sides. We don't have them for the Nürburgring lap. Not so much that it is a safety feature that we need, but the Nürburgring track will not allow anyway for a situation where in high speeds the car will start sliding. If that happens, the car will be on the gravel and in the rail anyway. There is not that runoff area like at Le Mans where there is a sustained situation at high speed where the car is sideways and then will start taking off. So it's still something that we may consider for the Nürburgring, but at the moment for pure performance, we haven't got this feature on. Also, we were on a single where we had the fin, which again was for safety reasons. I've removed the fin for lightweighting. We had a single pillar in line with the fin. Here I've gone for a double pillar, which gives us a bit more structural integrity. There's more load on the rear wing. And it's just a nicer, lighter way actually to create a structure for the rear wing. Okay, so let me switch back on the and go to the CFD now. Okay, cool. So we're back there. Just gonna stop Unity. Okay, let's dive in the excuse me. Let's dive in the CFD results now. So here you've got two platforms. One is AirShaper, which we are not using to develop the car. This is just a visualization of the flow around 424. And one is Bramble CFD. It's very much a professional CFD platform in the cloud, and that's what we're using to develop the car. And that's what I've used for 13 years. It was not called Bramble at the beginning. It was Total Sim, but they've basically changed the user interface, and it's become Bramble. Let me open AirShaper here. It's quite a nice tool to visualize the flow. Again, we don't develop in this tool. It's not made for a lot of iterations, but it's a nice way to see what's going on around 424 as an introduction. Here you can see what they call the 3D pressure cloud. So it's separations around the wheels and behind the car. Again, we wouldn't do much in terms of development with this, but it's a nice way to see maybe where the drag is coming from. But we sort of know anyway. The drag is always coming from the back of the car because that's where the most separated air happens. So think of the car as a wing, and if you want to increase your drag downforce point, basically you're just increasing you start increasing your rear wing and your diffuser expansion. That will straight away create more drag and downforce, and then you rebalance with the, once you know the downforce level at the rear with the drag associated that you want, you're working your design at the front to rebalance the car. Anything you do at the front doesn't affect drag so much, but it's there to rebalance relative to the rear downforce you've got. This is more like things that plots that we're using for development. So the static pressure on the surface of the car, and obviously under the car, you can see the suction level is very high. That's what creates the downforce. An important point here is where the diffuser starts. We call it the kick. So in front of it is a flat area of floor, and then the diffuser starts here. And if you can start the kick earlier, so more towards the front wheels, you will move that big area of suction to the front. This is a very nice way to rebalance your car. You cannot always do that. It depends how big. That's where the battery will be. So obviously there is a compromise with the size of the battery that dictates the floor to stay flat versus how early you can start your diffuser. In the modern Formula One cars, the whole floor now is a diffuser, so the kick is at the front of the floor, and the whole floor is curved. Versus the previous generation of Formula One cars, where the kick was actually at the rear axle or just in front, and most of the floor was flat. So here we got freedom to do what we want again, and you can see the performance is very good here with a lot of suction, and again the expansion ratio is a bit higher than what you see on the Le Mans cars. So I've increased here the height of the diffuser. You've got a nice, excuse me, a nice suction effect under the rear wing, plus the addition of these big end plates, which creates like a box section where the suction of the rear wing will be mirrored on the end plates and increase that suction in that area, which will also increase the suction of in the diffuser area. And then the front of the car, it's all about working that front wing as hard as you can. So first of all, I've explained that less volume on the wheel arch, we create these red areas, which is creating, downforce through pushing down on the front wing. But as always, it's all about what's happening under. And you see the blue, the integration of the blue is actually more important than the red over. So it's all this section, the suction happening under these, what we call turning vanes. This is managing the flow near the front tires, and how that, contact patch here of the tire interaction with the ground, how that flow will be managed. And I'll show you more about this in a minute. Surface friction is showing you mainly the velocity of the flow near the surface, and you can see how the flow is accelerated near the kick of the diffuser and also at the lowest part of the front wing. And in the areas of flow going over the side pods and not entering into the radiator area in this case. Okay, these are quite nice tools to visualize the flow, and you can move them as well. Which actually you can do things like looking at some rotational flow. So you see that what we are doing here with these die vanes, it's not so much creating downforce on the die vane itself, it's creating that rotation that then feeds air to the diffuser from the side of the car. I don't know if I can find a better view here. I think that one is the best. So you can see how the flow turns around the edge of the car with the die vane and the fine straight edge of the front wing. And this is all to do again with feeding air from the side, fresh air going on under the floor. At the same time, the air coming, let's go to the horizontal one. I think we've got a better view for that. That one is a nice view of showing that we have structure here. We've got flow working the front wing here. That flow is not used by the floor. It's going over the front wing and is basically extracted on top of the body through these channels here and this volume we have here. That allows us to, using the turning vanes on the side, to feed air from the side to the floor. And you see how then that air rotates around the fin in the diffuser area. So that's quite different to a Formula One car where just because of the shape of the car and how the general concept is. So all the Le Mans cars will work this way, to a degree. The floor air is coming from the sides, and the front wing air is extracted to the top body. In Formula One, actually, most of the floor or the diffuser air will come from the center of the car, and because it's just naturally working more this way, because they don't have the ability to manage the flow around the front wheel in the same way as we do for Le Mans cars. So just know that the way the flow structures are working is different. But all Le Mans hypercar will work more or less as you see here on this picture. And the game is just all about increasing these vorticities and rotational flows, increasing the structures, and pushing that suction level in the areas that you want. Okay. So I will exit now this platform, but this is a nice just visualization platform. But let's go to the Bramble CFD. If you want access to this platform, so this requires an account. But if you want access to this platform as a view-only access, I can give you access. Just be in touch with me, and if I have your email, I can create a view-only access to this platform. So here we have the results for starting run, 101. We've done about sorry, it says 49. Okay, we've done about 100 runs in 2022 to develop from the Le Mans to increase drag and downforce to get to the 424 for the Nürburgring. For each case, first of all, it's a test done at a certain altitudes. Here you can see 70-100 is 70 front ride height, 100 rear ride height, and a wind speed of 180 kilometers an hour, which is 50% of the top speed of the car. So it's a medium speed, and we always test at that speed. The speed doesn't really affect the results so much. It changes the Reynolds number a little bit. So any testing speed is valid, but I like to test in the medium area. You can see that sometimes we test at lower ride height. 10-20 is the lowest we test at, 10 millimeters, 20 millimeters. And the highest is 70-100. Most of the tests will be done at 40-60, which is what we call the design ride height, or where the car spends the most time around the track. So it's the medium ride height. It works for slow speed, medium speeds, corners. So all our testing is done at this ride height, and then now and then we do more mapping and different. We explore the map a bit further. So if I click on one of these, and then we can have a look at some plots. So that will show you some static pressure, very similar to what we've just looked at in the Air Shaper platform. And this is very much like the plots that I used through development. And you can compare, when we do a test, you can compare before and after the change. Excuse me. Okay, so again, if you want access to this platform for visualization, just ask me. So this is CP, and then you've got the same, but projected on the x-axis. Here is a scan, basically, of where the downforce is coming from. So that's a top view, and integrating from top to bottom, and showing you the integration of suction and showing you where the downforce is coming from. So front wing, rear wing, and the floor area. And then the same for drag, looking from the front of the car. This is similar to the noise plot we were looking at before. But the other thing that we are looking at a lot is the CPT movies. So this is, and I will look at it without the LIC. Okay. This is basically the flow around the car. So it's a section going through the car from the front wing. So you see the front wing here. And then as I go through, I'm sectioning through the car. So this is the nose. This is the dive plane. Now you can see the rotational flow on the edges of the front wing and the dive plane, as I explained before. So when it's red, it's obviously high energy flow. So either high static pressure or high velocity combined. And when it goes to blue, it's separated flow with less energy. So everything going inside the car is turning into blue quite quickly. And in fact, around inside the wheel arches, it's dead flow. We call it, there's no velocity associated to it. Remember the story about isolating the flow from the wheel arch? So on here, there is still, you can see bodywork, but as soon as we are getting to the suspension area, now the bodywork has disappeared, the suspension legs, and the flow is free to go inside the wheel arches. When we did the Pescarolo car, we had that face continue further, and I explained the story about isolating the suspension was very difficult. And I'm glad that we've learned that lesson and developed around a much easier concept to develop now and to deliver. Here you see the contact patch of the tire with the ground, and typically that what we call the jet of air. And this is something we want to control with that dive vane here and the rotational flow. It will be very much about what the wake of the front tire, where does it go, and how does it impact the floor at the back. Okay, you can see how that rotation has taken some of that wake with it. Okay, and then I can continue. Okay, now you can see the air coming inside the radiator. First of all, the air going inside the car will always be much slower than the air outside the car. It's a ratio of about 1:4 or 1:6. So 4 or 6 times slower the air going inside the car, just because it's going into an area of high pressure and slows down quite quickly. And we are measuring through these faces, where the radiator will be. We've got a delta pressure, and we are measuring the mass flow of air going through that. Going to the diffuser area, we've got a very powerful rotational flow. These fences are extremely important. If we remove them, a lot of performance will be gone. And we test, typically I will do 10 millimeters, shift left to right to assess the sensitivity. When I change the top body, I go 25 millimeters steps. But when I touch something under the car, it's more like 10 millimeter steps because it's much more sensitive. You see, we have the braking system as well. So the flow is going through the discs as well. So it's fairly accurate model. Here we have all the suspension members and the flow going through the brakes as well. So this is the brake ducts, and that's coming from these ducts here. That's the inlet to the brake ducts at the rear. Okay. So every test has got a simple name. In fact, we have a DRS open here test. We can have a quick look. A DRS open. If I select two tests, and then I can do the CP plots. Oh, sorry, I'm going to take a lateral movie of CPT. Now I've got two movies. and I can scroll through, and you can see the DRS is open. You see the flow here, and the DRS is closed here. Just show you how you can compare quickly what's going on. I think there's a question here, so let me. Yeah, Bautista.
Yeah. At some point you mentioned that so you're trying to introduce some flow onto the diffuser coming from the side.
Yes.
Yeah. Is there a risk of I don't know, maybe having some losses from that air coming from the side, which may be less clean than the one coming from the front? How do you control that flow coming from the side? And yeah, also when you were going through the sections just before, we're seeing some green areas on the floor. I don't know if maybe you can do a quick explanation of how these areas are generated.
Yeah. So first of all, as I said before, first of all, the fact that the air comes from the side to the floor to the diffuser, in a way, that happens from the first concept, because these cars work like that. If you design a Le Mans car from scratch, the diffuser will suck air from where it can, and on these cars, it comes from the side. And actually on F1 cars as well, from the second part of the diffuser, it also comes from the sides, purely because there's a lot of suction and a lot of air needs to go there, and it needs to come from somewhere. And so what you find is you're not really deciding that the car is going to work like this. What you're observing, that the flow structure is working this way, and all you're doing with development is making the best use of that structure. And that's why we have fences here, or the famous skirts on the old F1 cars. You can see the effect it has, because air wants to enter anyway from the sides.
Yeah, exactly.
And what you do is you're not going to change that, because it's a whole pattern of suction and high and low pressures. It would take a completely different even regulation set, or to remove the wheel arches to change that, and you're not going to do that. But what you want is to go with the flow. Actually, that's you want to go towards what the natural flow wants to be, and you want to increase that movement. So the nice thing on the Le Mans cars is the sides of the car is very clean. If you look at the flow before that, all of that red, the lower part, not so much the higher part, is very clean. So this is good air to come and use. This is good air. That's air you want to enter into your diffuser anyway.
Yeah.
Having said that, the reason it's clean because if you look at, it starts from the side wall of the front tire. What you do in front of the front tire, what you do here with the edge of that, the edge of the front wing, and on the F1 car is the same. They play with little details of geometry, because what you do there will impact what's happening on the side of the front tire, and then further it impacts on this window of red here. And if I'd go further back in history, it wouldn't be as clean as it is now. It's, for me, when I see a lot of reds and wanting to push inside, I'm really happy to see that. I know it's performance for me. It's when you have red flow, which is, again, in aerodynamics term, it's like high energy flow.
Yeah.
Then if you put fences on that, or you put edges for it to turn around, it's going to create a lot of suction. If you do the same in the green zone and put, say here you put a wing profile, it will be very, very weak. It will not do much.
Yeah.
Because a fence or a profile in a low energy flow, it will be like it's the difference between you having your hands inside the car or putting your hand through the window and seeing the pressure pushing on it.
Yeah.
It's exactly the same. Your hand, when it's in the green, okay, it's moving a bit. In the red, it's a lot of pressure. So whatever you do there is very, very powerful. So what you want to do is protect that area here so that it's ready to be used by some aerodynamic devices like fences, wings, whatever. The same for the rear wing. All we do with the rear wing is make sure the flow before the rear wing is very clean. You see all that nice red. That's why rear wings now on Le Mans cars are fairly high. They used to be much lower in the olden days.
Yeah.
And they used to extend at the back. And I have people sometimes saying, why on 424? Let's go low and at the back like the old Group C cars. But they didn't have CFD and as much testing time at the time. But what you find is the rear wing wants to be high just to work in this very high quality, high energy flow. And then it's like you put the wing in the best environment possible for it to work its best.
Right. Yeah. Yeah.
Yeah.
Great.
So what you do on the difference between F1 and Le Mans for in this case is mainly, I would say, that section in the middle, the front wing is working hard. And then you've got the ability to, oh, this is a test with a floor that was not a straight edge. I didn't keep that, by the way. But the floor starts and divides the flow that's not very high quality. You've got lower energy flow, and you're trying to keep only red under the car going under. In fact, that test didn't work because you're sucking some of the bad low energy flow under the car by opening that mouth. But in F1, the floor starts much later. There's a lot going on before the floor in F1. All on the side of the chassis, there's no floor. So they're doing various rotations to attract more high quality flow going on there. They have more space to do that. So it's a bit different. But the philosophy is, well, the idea is the same.
Yeah. So you're introducing some vortices to bring that high energy flow from the side to feed the diffuser.
Yeah. In fact, that's all what the dive vane is doing. It rotates.
Yeah.
Sort of takes air from the top down in the right way. You can see it's sort of pushing that blob of blue away. And it's just making sure imagine air is coming from quite far away, actually. Well, a bit further away from the car, back towards the car because of this rotation here. If you didn't have that rotation, that blue would be much lower. And then suddenly you would suck some blue further down. This wouldn't be as clean. It would start to be very green-blue. And the result would be the CP under the car. You see how it's sucking a lot here on the side of the floor? That wouldn't be there. And it would be green, it wouldn't be blue. And at that point, it's interesting how, when you create an area of suction, it sucks more on the surrounding areas as well. If you lose suction on the edge, you lose suction in the whole diffuser.
Yeah. Oh, that's great. Thank you for going through the different sections.
Yeah, no problem. So we won't have time to go through all the details here, but what you can see is you can reference any test. So the way it works here is on the platform is you've got assemblies, you've got parts, and basically parts are underfloor 3 to 1 body. So you recognize the name I use in Onshape. These are basically assemblies from Onshape. Body, underfloor, body. Each time a part has been changed or an assembly has been changed, it's imported here. And then in the assembly, we go here, and then we create a full car assembly without the wheels. The wheels are in a separate part of the system. And that will basically be made of an underfloor, a body, a splitter, a rear wing, everything that makes up a full 4x4 car, which mirrors into the Onshape assembly level. You've got more to that platform. We've got kinematic setup, so we effectively give the system the location of all the kinematic points of the suspension arms so that the suspension can move up and down when we test at different ride heights. And then the runs are set up in this section here. In fact, in the run section, you can see the branches are referenced here. So B50, B49, V169 versions. So that reference back to Onshape. And all the geometries are stored in Onshape and here as well. So there is traceability on all the geometries that have been tested. The great thing with this system as well is, let's try and find an example where I have done some cornering mapping. Okay. Let me widen that window again. In this case, for a given geometry, I want to test at more than one attitude. So I test at 40, 60 ride height. Remember, these are our design ride heights. In a roll condition, so the car is rolling now. So it's got a roll angle. In a steer condition, so the front wheels are steering. And in a yaw conditions where from the top view, the car is actually at an angle relative to the wind, which happens in corners. And then we have a yaw steer roll combined. This is, I do that sometimes to get sensitivity to not only ride heights, but also the cornering attitude of the car. So remember, these three parameters, yaw, steer, roll, and then the ride heights, front and rear. So we've got 5 parameters that affects the dynamic, the aerodynamics of the car for a given geometry. So let me now move on to, and that will feed into the aero maps that we'll talk about in a minute. So I'm conscious of time, so I'm going to try and accelerate a little bit here. Here you've got 2 spreadsheets, and they're both doing the same. They're storing all the results since the start of pairing. So if I open there and you go into CFD dev, every line is a CFD test. Every orange line is a baseline. In fact, it's written here. And in between baselines, we do individual tests, and then we create a new baseline. Remember the video I was showing at the beginning? They were a combination of all the orange lines. This started on the 30th of March, 2011. First ever CFD test for a pairing car. And that spreadsheet covers all the testing up to (2014) May, including the Pescarolo projects. And then we had a bit of, I had a time where I did an F1 model. So I had some Formula 1 testing done here because we got more credit this way. And then the CFD stopped at that point, so 2015. But on the video I was showing was these 2,300 runs. And for each run, it says what ride heights we tested at, yaw, steer, roll, the speed in meters per second, the density of the air. And then we have SCX, SCZ, which is drag downforce at the front, downforce at the rear, L over D, aerodynamic efficiency, and then the aerodynamic balance. And it goes further. We've got deltas to the baseline. We've got the radiator M dot, which are the mass flow through the radiators in kilograms per second. Again, the cooling of the engines, and then more. We have the brake cooling and all of this. So these are big tables of data. Let me open the 424 one here. This one is the one we did in 2022, and hopefully, and by the way, I can't wait to restart the CFD testing when the resources come back for that specific analysis. But in March 2022, we restarted CFD in the Bramble platform. If you look at the L over D, it was 4.8 here for a drag of 1.28. That was the first Nürburgring specific starting concept, if you like, taken from the LMP1 Le Mans, and just adding that rear the bigger rear wing and the new diffuser, and then starting CFD. And then over the course of a few months, up to August 2022, and 100 runs, we end up at an L over D of, in fact, 6.08 here, which is higher than the 5.5 I mentioned, because some of these developments happened after the update on the Unity. So there's more performance in the pipeline, but you can see basically the progression of the performance, and the drag level is 1.3, so not changed so much from the start, which was 1.28, nearly 1.3, but the downforce level went from 6 or 6.5. At the end, we are nearly 8 on SCZ, so very high. That's when the DRS is closed. And here I log everything. So when you have cornering analysis, you've got yaw steer roll and yaw steer roll combine, which we looked at in Bramble. I do tests like the low ride height, which is the 1020, and the high ride height, which is the 70-100. And then we've got other tests, other ride heights. You know, we also test at 2560, 5560, just to fill in the map. And we've got what we call takeoff tests as well, where the ride height is extremely high, 115 mil, because we had situations where the front of the car, the tires were losing contact with the ground at the Nürburgring, and the downforce turns into lift at the front, and the car starting to take off. So we had to look at this in CFD very closely. And we've applied some speed limiters around the Nürburgring to go and counteract this problem. Okay, so obviously this is not the end. You know, there will be much more CFD analysis done, but this is how Perrin is going about it. And when we get more resources soon, we can carry on doing CFD testing. I think there was a question, maybe. Anybody's got any question about this section? Okay. So I carry on with this. So once we've got our logbooks full of data from CFD, then we build the aero map. And again, you've got access to this. And the 424 aero map is coming up with a model that will define the behavior of the car at various ride heights. So that can then feed into the driving simulation, because at the end, the aim of all of this is to create the best vehicle model we can that we can drive and let our test drivers go around the track and see what the lap time is and keep developing this way. So the way we do this, there's multiple aero maps that were created in 2022. The latest one is the 424 aero maps here. You've got results from CFD in the middle. So each map this is front downforce, SCZ front. And all the points here are tests from the CFD Bramble tests, okay? So I said the middle part of the map is 40 front, 60 rear for us. But we test, I do sensitivity analysis in both directions. So changing only the front ride heights here and here, and changing only the rear ride heights. We do the very low ride heights test at 1020. We do the high ride height at 70-100. And then we do the takeoff ride height when the front is basically going over, you know, it's going to very high levels, 115, 160 millimeters. It doesn't sound like a lot, but for such aerodynamic cars, it is very, very high. You can see actually that the downforce is completely lost at the front. And it might turn into a negative number at higher numbers. So that's where the car will be pulled up in the air. We do the same for the rear downforce. The balance, aerodynamic balance, very important number. We try and keep an aerodynamic balance around 44%. It's very sensitive to the front ride height. You can see it's going to 50% at low ride heights. And when the front is high, we only have 34%. So it's fairly sensitive to the front ride height, as always on these cars. And then the drag. And basically what I do here is I create quadratic equations. So for front downforce, rear downforce, and drag, I come up with a set of parameters and quadratic equations that are a function of, so there is a constant number, there is dependency to the front ride height, to the square of front ride heights, and then rear ride height, square of rear ride heights, the yaw, steer, and roll as a linear number. And then if the DRS is open. So here you can see when you open the DRS, what it does is it does nothing to the front downforce. It reduces the rear downforce by 1.5 SCZ. So over a number of 4.1, it's about a third. And the drag is reduced by 0.332 SCX, which again, over 1.3 is also is 25%. In fact, if I apply DRS on this model, I put a 1 here, the map is changing, and you can see the drag is now 0.992. If I remove DRS, it's gone back to 1.324. So these maps here are expressions, are calculated from the expressions of these quadratic models. And then I do a difference between the CFD maps and the model for each ride height pair. And I can only compare where we have CFD results. And then we look at the differences between CFD model and the dynamic model we'll use in Unity in percents. And obviously it's not perfect because we are applying a surface and we're using equations. We're not using table of data. In fact, these are sections through these maps, and you can see the points we're testing at versus the model, which is the curve. So yeah, the curve is fitted around these points, and it's not a perfect fit, but it's not bad at all. And we have differences of, 4% either side, 1% here, 3% here, 2%. So overall, the average is very good across the map, but some points are 2% out, 3% out. But around the lap, it will even out between the plus and minus. This is the analysis of where the 424 spends time around the Nürburgring. So every blue point is a point around the track. This is front ride height, rear ride heights. And I'm just checking here that we're testing at the correct ride heights. So basically the car in low speed will be in this region when the car is high. And in high speed corners or in the straight line, it will be very low. And in medium speed corners. So you see how the car goes up and down, and there is a spread because there is a bit of pitch movement as well. But you can see that the map is fairly well centered. So our main point of testing is 4060, right in the middle of that cloud of points. And then the spread of the map as well. You can see why the testing points in CFD have been chosen this way, just to cover that sort of cloud of points. This is a nice way to look at it and check that we're testing at the right attitudes. Okay. So then we are left with a good quadratic model that creates now automatically the aerodynamic outputs, the aerodynamic numbers for any kind of attitudes. The model goes a bit further. We also have this section is important, is the front flap angle model. So when the flap at the front moves, it affects the front downforce. So first of all, we have a static angle that we can set when the car is not moving. We also have an angle change when DRS opens at the rear. As I said, as soon as DRS opens at the rear, we do a change of 13 degrees. We drop the flap at the front by 13 degrees. And then we also have, this is the sensitivity of front downforce per degree of flap, okay? And then we have the set, which is at 0 degree flap angle, how much downforce we have. We also have a model of the flap is fitted with a preloaded spring. So it's like a narrow elastic effect. So in high-speed corners, the flap will be pulled down by the spring, and the spring has got a stiffness of 0.008 degrees per Newton of force on the flap, and we have a preload on it. The idea of this system is that naturally the aerodynamic balance, remember, as I explained, when we go to high-speed corners, the front goes lower, and the aerodynamic balance naturally is going forward because there's suction going increasing at the front of the car versus the rear. That can lead to an oversteery car in high speeds. So by having this spring, the flap drops, and naturally that 50%, if we wouldn't drop the flap, the aerodynamic balance would be too high at the front. But because the flap is elastic, the aerodynamic balance is moving back to the rear automatically at high speeds. That's even before the RS is open. So you see there's a lot of details and work that's gone through developing these systems. It was a combination of spending time with our test drivers, going around the Nürburgring, complaining about the balance in high speed versus low speeds, and then working the DRS activation and how to best use it just to optimize lap time. And we needed to have this aero map model so we could keep upgrading the car and then let our test drivers drive the evolution of the aero maps. Okay. So before I finish and I take a few questions, once we've got everything, we go to our dynamic simulator. We enter all the numbers that I just given. So we enter all these numbers into Unity, and Unity will calculate dynamically, you know, SCZ front, SCZ rear, the drag, the balance, based on, and we have also the effect from the steering angle, the yaw, the roll. Everything links back to it in Unity. And you've got a full dynamic model ready to drive in Unity. And I'll stop here and I welcome any question. I've covered from start to end the aerodynamic development and process for 424. But I welcome any question in the last 10 minutes that we have, and see if you want me to explain further any details, any points that I've been discussing today. Anybody has got any specific question? You can also put your question potentially in the chat if you want. Okay, Bautista, thanks.
Did you encounter some other similar surprises as you had with the Pescarolo model, where you had an idea of something that would work, in the end it was completely the opposite, or yeah, kind of a mistake?
So yeah, okay, thank you for good question, and I like that, and it comes back to the concepts that you're choosing to develop, where it goes, and it's really fundamental to the success or not of Formula One cars on track today. And I'm somebody who, luckily, apart from the front area, that's again, I try to create these idealized sealing surfaces. Luckily, I'm fairly pragmatic when it comes to an idea versus what we can deliver. You know, we always say an idea is as good as who's going to deliver it. Like, can we deliver the idea? It's the same for aerodynamic concepts. Having an idea is cheap, is easy, but to take it, to develop it, and deliver it is difficult.
Right.
And to be honest, through my journey, and you've seen it's been a long journey, and that's why, and I hope, you know, and I know the day 424 exists and people see the performance of it, they will realize, you know, the quality and where it's coming from. And you can see, hopefully today, even more, how much work's gone through it and how much experience is needed to achieve it. But I have to say that journey has been, from an engineering point of view, for me, it's been really fantastic to be able to drive this and learn from it. My main learning, I explained them today. And yes, the front of the Pescarolo was, you know, it's been a bit of a blow because I think it set the Perrin brand a bit back at the time, also because the car didn't perform as well as I wanted, and it's a time where Pescarolo stopped as well. Everything was a bit difficult, even though the relationship with Henri has remained amazing, and it's a great experience. But you see the cost of not having the right concept is huge.
Yeah.
Because you will only know it at the end, you know. And I'll be honest, apart from that, there was actually, I will tell you another one. This picture here is at the time of the Pescarolo car. It's just before, in fact, if you look at the Pescarolo car, you will recognize the front brake duct inlet was that shape. And I used to that top bodywork that covers the suspension, I was trying to push it as far backwards as I could. So you can see there's because I wanted the front wing to be very uncovered.
Yeah.
Now, if you look at the modern hypercars at Le Mans, the bodywork extends a lot to the nose. It's covering the front wing a lot. And coming from F1, I wanted a front wing that was uncovered. It was a concept that I believed in. And to be fair, you see these blue areas in the corners?
Yeah.
When you do that, when you move that leading edge backwards like I did, it creates a very aggressive flow. That's because there's a lot of high pressure in front, and then it pushes the flow nearly vertical, and then you have to go around that bodywork, trying to then make it to follow the bodywork towards the suspension. And I believe on the Pescarolo we had two problems. First of all, that sealing near the suspension didn't work, and also that aggressive flow, which was attached in CFD, the flow was following. I believe on the Pescarolo it was not, and it was shooting up. So that's another mistake I did at the time, because in CFD sometimes you will not separate the flow as quickly as in the real world, or it can be the opposite, but I've seen that. So that's another learning of not pushing, and it was not required. I could have extended the bodywork further forwards, and it would have been an easier path for the flow to go around, and the performance would have been very similar. So it's a learning as well of questioning always what you're seeing in CFD and thinking, can this translate in reality? And in this case, it couldn't. When you do the same under the car, it's different because you've got the ground effect is helping you. When you have to go around aggressively around geometry under the car, the ground is actually helping you do that.
Of course.
Because the proximity of the ground is actually helping the flow go where it needs to go. On the top body, it's not true. And I did a mistake there. And apart from that, honestly, the rest was very sound. So now you see on 424, the top body, I don't have the picture here. On here, you can see the top body extends now further forwards.
Yeah, indeed.
Yeah. And the brake ducts is now under. It's an easier path, and there's less risk of separating. The rest of the car is extremely sound, and now the front as well. Like there's the risk of not delivering the performance is extremely low now, and there might be other, learning still. But the rest is very conventional, and to be fair, now you see a lot of hypercars at Le Mans. They follow the same philosophy. I think of a car, the Audi R15. I don't know if you remember that car. Let's have a look quickly. I like to show that car because is it the R15? Let's have a quick look. Yeah. Do you remember that car?
Yeah, I mean, I didn't watch the race, but
yeah,
I do. Yeah, I know.
They did two versions of that car. I really love that story. In fact, you've got the 2008 version here, and you've got the 2009 version. What they did in 2008, and it was that they kept the name of the car is the same because they kept the chassis exactly the same.
Yeah,
they've changed the bodywork around. This is a very good example of bad concept and then good concept. And the bad concept was the first version. Look at what they had: a very intricate management of the flow towards the back. Maybe that picture is a bit easier to see, but you see the inlets in front of the rear tires. They were channeling air back, a bit like in single seaters or F1, because there's no bodywork around the rear tire. They were channeling air back towards the inside and entering again and having that channel going around. And that channel was then in the suspension area at the back with loads of holes and not the ability to seal it properly as well.
Right.
They had a very complicated, loads of piece of bodywork inside to try and make that concept work. Didn't really translate at the end. And what they did is, look, they went back with a much simpler version. That slot is much smaller. It's just for the rear cooling now, but it doesn't operate as a big flow structure for the diffuser or floor anymore. So they went back to a much more simple concept at the back. That car was much easier to drive for the driver and stable and all of this. And I remember looking at this, and it was the time where I was doing this learning with 424 or the LMP1 car. And I love this story because it shows, good concept versus bad concept. And again, you see the first version here, you see these big slots. It was very intricate. They were trying to do a lot of louvering on top because the regulation were asking them not to look at the floor from the top. So they were doing all sorts of little tricks with bodywork to try and get passage of air but the reality is it was a complicated, not only it's not that it couldn't work, but to develop that, the number of parameters is extremely high because every piece of bodywork can move up and down individually.
Exactly. Yeah.
Instead of having a more, I call it like a more solid, a more structured design that a bit more is together. And I really believe that even in F1, you see the good cars are actually a bit more simple to the eye sometimes, and they are developed in the right areas.
Yeah, definitely. Yeah, that's super interesting. Yeah, it's kind of like keeping it simple is the best way to go sometimes.
Yeah.
And,
Yeah. Another, we can go around with. Do you remember the Nissan LMP1?
yeah, which completely failed.
Completely failed, and they had an extremely complex aerodynamic concept on this car. It's going to be hard to see on these pictures because from the outside it looks fairly simple.
It had some tunnels going inside.
Yeah, the air coming in was going all through the car through tunnels.
Yeah.
And I know the principle. Like it came of a concept that didn't know there was going to be suspension in the car. So the tunnels were sealed all the way to the back of the car. Let me try and show you the aerodynamic tunnels themselves. Here you go. We can see them. That's at the back. So that tunnel here, you can see even you can see through the front. You can see some light at the end.
I remember. Yeah.
You can even see how it's meant to work with these pictures here. The problem is, where do you put the suspension? The suspension has to go through. So then they designed a suspension that was extremely unconventional, quite heavy. So the legs would be either side of that. And it meant that the car was extremely heavy. Obviously, they had the front engine concept because they thought you can create more front downforce than rear downforce on these sort of cars. Anyway, there was all sorts of flaws from the conceptual point of view, which, by the way, I could go on and on. I mean, the last one for me is the Peugeot 9X8. And I'll finish on that. As it comes back to conceptual decisions, the Peugeot 9X8, they decided we don't want a rear wing on the car. Yeah. By the way, this is not even a decision made by aerodynamicists. This is a decision made from a branding point of view.
Right.
And I respect that. They want to transmit a certain image. But the fact is, there's a good reason why, cars have got a rear wing. It's a natural way of creating that wing profile, from start to end for a race car. And they said, okay, we can counteract this by having an aero balance that will be more to the front, so a 50-50. So we need to use big front tires so that we can use that aero balance, a bit like the Nissan LMP1. But when you do that, it's a race car is not meant to be 50-50 with the same tires front and rear, because you're going to struggle to warm up your front tires by doing that, because there's more power at the rear, and the power on the drivetrain will warm up the tires naturally at the rear. So you end up with a very split temperature front to rear tires, and the front don't work, and you've got understeer. So you can see the aerodynamic concept has dictated the mechanical vehicle dynamics and in the wrong way. What's happening is this year they're coming up with a car with a railway. Yeah. But the cost of that learning is huge. It's meant that they haven't had an optimum car from a vehicle dynamics point of view for the last year or two. So interesting stories that we need to learn from. let's remember, motorsport is not about having an idea that nobody's ever had before. Motorsport is about performance, and there's a good reason why cars are designed the way they are designed. And if you want to beat the best car, for me, when I look at the Porsche 919 that we're trying to beat at the Nürburgring, actually it's a very similar concept to what we're doing with 424. If you want to beat the best car, try and understand what they've done first and then do a bit better than them. But we should remember that you can't design it back to front, because it will not make you, people have tried that in the past and it failed.
Yeah.
So in fact, for me, finding good engineers and people to work on 424 with me, it's not a game of trying to find a new clever idea. Is more on people who understand the philosophy of unit testing, optimization of a concept, and just keep going at it and keep simplifying. If anything, I want to remove things from the car. I don't want to add. Yeah.
Right. Yeah.
It's the same for aerodynamics concept. If somebody can come to me and say, I found a way to, well, you will not actually find a lot of examples on 424, because there's only, for example, one dive plane at the front, under the front wing. Some people put 3 or 4. If somebody would come to me and say, instead of 2 dive planes or fences under the front wing, I've put a bigger one, a single one, and the performance is the same, I'll say, let's go for it.
Yeah.
Then I know we've got less parameters, and less parameters mean we can do bigger tests where we move one bigger geometry and the sensitivities will be bigger, and then we'll optimize that to a bigger, faster, and to a higher performance level before we add more complexity. This is a massive thing for me. And I'll train people working on 424 to think this way with me, because we'll go a long way by developing this way. And at least we don't get lost into too many parameters that we don't know how to make to change, or how to develop it. And if you have so many parameters, you need then a team of 100 engineers, to develop every aspect of it.
Sure. Yeah. Completely. Right.
Okay.
Yeah. No, that was super interesting. Thank you.
Cool. I'll take a last question and then I'll wrap it up. But yeah, again, it's gone really quickly to cover everything. But I hope you learned a lot today, and we'll keep. I'll do more sessions anyway, as you know. But aerodynamics is a big topic for 424, and I really encourage you to get in touch with me if you want access to Bramble or if you have any question. So I'll take a last question if you have. Otherwise, I'll wrap it up here. Okay, Axel, please.
Yeah, sorry.
Yes, sure.
How do you feel like the fact that any of the CFD that you've done has not been validated with either like wind tunnel data or whatever?
Yeah, thank you.
Like
for that question.
Yeah.
I'll show you a car that I worked on. I was aerodynamicist on that car. I designed that car, in fact, in terms of aerodynamics. Well, we split the car in two because that car set an electric record at the Nürburgring in 2016. It's like designed as a race car, but it looks a bit like a Ferrari, but road car, if you like. But under the bonnet, it's like a race car. It was a bit heavy. It was electric and 1.6 ton, but they wanted it styled as well. So I said, look, we're splitting the car into everything under that line, and the rear wing is mine, and I do the performance level, and then the top part was the style. But that car was designed using Bramble CFD. It never went into a wind tunnel, ever. We did a full year of CFD development with Total Sim and Bramble on this car. I was in charge of that. And we built the car, and then I was the race engineer for the following year when we went to Nürburgring. We went to COTA, Circuit of the Americas, to do a records as well. And what we did is we fitted, like we always do, strain gauge on the push rods, and then we measure downforce at the on a straight line on an airfield, which we will do for 424. And it came inside 5%. When I say that, it means we measured downforce level with less than 5% error at different attitudes compared to the CFD. That was a big validation for me because this is the tool that I'm using for 424, you see? So yes, it's extremely difficult to be always sure of correlation between CFD and reality. It relies on two things. First of all, I trust the people at TotalSim and Bramble because I know them, I worked with them, I did this project and it worked. And they have a lot of experience, so their tool has been developed to match reality as much as possible. But it will depend on each project as well. Remember the Pescarolo project I did, it didn't match at the front because I took some risk that CFD, where I took some risk with the design where CFD and couldn't predict well enough the performance that actually we had on the track. So it doesn't always work, but it's also linked with experience. You know what can translate, what cannot, and then you don't want to take these risks as much. And that's what I do now with 424. So I'm extremely confident with 424 that we have a very sound concept that will translate. There will be some learning for sure, but the strategy with 424 is like with the Neo EP9. We're gonna take the CFD, build the car, not go into a wind tunnel. We'll go to the track. We're going to do measurements there. It allows you to measure more than the aerodynamics, to validate the powertrain. It limits the amount of testing. If we're outside the 5% margin on downforce measured, then we might go to a full-size wind tunnel or even a more controlled environment. They have TotalSim has got a tunnel that you can test the real car inside, as in driving in a tunnel at speeds. Or you go to a full-size wind tunnel and then you start measuring in a more precise way and then look at the flow on the surface and understand where it doesn't work. But that will be the strategy. But if all goes well, we go to the track and it measures inside the margin level that is acceptable, and then we don't even think about any potential issues because we know it works. And at this day and age now, with the computing power and the CFD tools we have, it's a very good methodology to use. Okay,
thank you. And just if I can add something, what's why you don't want to, like, for instance, take like a reduced scale model and put it to wind tunnel?
It's purely a cost.
Yeah, cost.
Yeah, it's a cost, and it's also, I'm building a team and thank you for your question, because it comes back to the essence of what pairing is and how we want to develop and the vision we have. It's a digital team first. The great thing with CFD and digital is this is the team I want to build, because that's where the people can access what we are doing live. We work in the digital space. CFD is a natural way to develop for us. If we start doing wind tunnel testing, we are bound to one location, to the physical testing. It's harder for people to access. Yeah, you can do videos about it, but it's not the same. I want a team where it doesn't matter where you are. You're part of it. You can plug in very quickly and develop with us. So I don't want two parallel way of developing. I want just the one strong CFD way of developing. And we will also learn about correlation. If there is any issue, we will help develop the CFD tools. We will invest, I'd rather invest time and money into the digital testing platform rather than invest time and money into the physical testing platform, because the future is digital anyway. And yes, of course, we go physical at the end with the product that we build. But as time goes, the product we build from the digital testing will be good to go with very little testing and modification needed. So it's a philosophy, it's a strategy of where we want to put our energy.
Okay, yes, understood. Really interesting point of view. Thank you.
Okay, I'm going to wrap it here. Let me close this. But yeah, I just want to say, really enjoyed. Oh, it's frozen here. Okay, really enjoyed the opportunity again to talk about 424 in details with you tonight. next session is next week and will be vehicle dynamics. So yeah, let's keep going, and I hope you enjoyed it, and that will and we'll keep talking next week on the next session. Thank you, everyone.
Thank you.
Thank you.
Bye bye.
Thank you. Thanks for your feedback on the messaging. Appreciated.